This video deals with GRAM SCHMIDT method. This method here you can see in linear algebra. If you open any book or videos, you see this method here. What consists this method? Suppose I have, for instance, let's work on R3. Okay? Suppose I have three vectors, A1, A2, and A3. Now, the GRAM SCHMIDT method, we transform this vector in Q1, Q2, and Q3, in which Qi dot Qj is equal, will be 1 for I is equal j, and 0 for I different from j. So this form orthonormal basis. So let's write here. Okay. Orthonormal basis. Or standard base. Standard basis. Okay? Now I'll write down here. See? This is my Q1, Q2, and Q3. Okay, I will not put the arrows in Q1, Q2, and Q3. You already know. Let's call this axis Y1, this Y2, and this Y3. This is an orthonormal basis. Q1, Q2, and Q3. Repeating, my intention is to transform, okay, for instance, three linearly independent vectors, okay, to transform in a standard orthonormal base or standard base. Okay. How we are going to do this and why we are going to do this? The application of GRAM SCHMIDT method we will do in the last part of this video. There is an application for this. Okay? To understand the next steps that we are going to do, it's better for you to pay attention on this. Suppose I have a straight line and I have a vector v. Okay, I'll put an arrow here. Okay. What is the orthogonal projection of this vector on this straight line? You see, it will be this segment. Okay. This is a scalar. So here we have this projection. Okay, v is projected in this segment here. Look, this is alpha. This is hypotenuse. Okay, so this segment here, let's call AB. AB is a segment. Okay, is the magnitude of this vector v times cosine of alpha. Okay, this is AB. Now, suppose instead of AB, we want a vector over here. Okay? Now, consider a unit vector here. Okay? Let's call Q1 or Q2 or Q3. Let's say Q1. I'll put an arrow here just for you to explain. Look, I will do the dot product of this vector v dot Q1. So this is equal to magnitude of v times magnitude of Q1 and cosine of the angle between Q1 and v. So this is 1, so this is equal to v cosine alpha, which is exactly the segment, the scalar. You see, this is scalar. The scalar of the segment AB. Suppose we want the vector AB, not the scalar. You just take V cosine alpha, and here on this straight line you put the unit vector. So there's the vector AB. This is very, very important to understand the steps that we are going to use to find GRAM SCHMIDT method. Please look at this carefully. Now, here we can substitute this like this. Look, V dot Q1. Look, see, this is V dot Q1. I put here Q1. So this is a vector AB. This is scalar, okay? Because Q1 is a unit vector. It's clear, it's quite clear this. Okay, then we can go one step ahead. Consider the vector A1 and A2. Obviously, they are linearly independent. Here I have vector A1 and here vector A2. The vector, okay? Look, as I said before, I will not use the arrow. Okay? Now, you see, I will do as follows. A1 is not a unit vector. So, from here, I'll get Q1 is equal A1 divided by the magnitude of A1, which we know that's A1, this is square root of A1 dot A1. Now, I guarantee that Q1 is a unit vector. Any vector divided by its magnitude will be our unit vector. So here we obtain Q1, just doing this. Now, we can do as follows. I will project A2 on this straight line over here. So see, I will do this. Okay, this is K1, okay? I'll write down there. Okay. Let's increase a little bit here. Let's suppose A2. This is A2. Okay? Now, I'll project A2 into this straight line over here. That's perpendicular. Now, you see, look, this here, the size, the magnitude, this will be A2 dot Q1. See? A2 dot Q1. Just we did before. So this is a magnitude. Okay? Now, if I want this vector, I'll just multiply this scalar quantity times Q1. Okay. This is a projection of vector A2 on this straight line, okay, in which K1 lies on this straight line. Now, here is the scalar. If I want the vector, you see the vector, I'll just put K1 over here. Now, look how interesting it is. This vector here plus this vector here, let's call this vector here K prime 2. See, the K prime 2. Look, this vector plus K prime 2 is equal A2. So A2 is the resultant. This is the sum of this vector with this vector. So A2 is equal A2 dot Q1, so this is a vector, plus Q prime 2. Okay? You see that Q prime 2, or Q2 prime, is perpendicular to Q1, which is good. You see? Now, Q prime 2 is equal A2 minus A2 dot Q1. It's easy. Now, Q prime 2 is perpendicular to Q1, but its magnitude is not necessarily 1. So then Q2 is equal Q2 prime divided by the magnitude of Q2 prime. You see how easy it is? So Q2 is equal Q2 prime. This is the square root of Q prime dot Q2 prime. Now, I guarantee that these vectors, these two vectors, A1 and A2, okay, which are not orthogonal. See, this is A2 and this is A1. Okay, this is A1. Now, I transform using GRAM SCHMIDT method into orthogonal vectors and also into orthonormal system, because I'm working the plane. See, this is a plane. Okay, this is a plane. It's clear now? Now we will do in the space. Okay? Now consider these three vectors, A1, A2, and A3, a basis of R3. So these three vectors, non-orthogonal vectors, they span R3 because they are linearly independent. That's why they are a basis of R3. Now find the orthonormal basis, Q1, Q2, and Q3. Now, do you remember when, suppose, with the two vectors, we got Q1 and Q2, okay? As we did before, this is Q1 and Q2. So the magnitude of Q1 is 1, the magnitude of Q2 is 1, and this is perpendicular. Let's call X Y1, Y2, okay? And this, let's put Y3. Now, here is the third vector, A3. You see, did you understand? So previously, what you did with A1 and A2, you just got Q1 and Q2, okay? We did that. Now I will work Q1 and Q2. They are perpendicular, see? They are here, perpendicular, okay? That's a plane Y1 and Y2. Now, what I want now is to obtain Q3. Now we know, if we use the dot product of this vector A3 to Q1, I will project this vector on this Y1 axis. Okay? You see, look, I'll repeat again. The dot product of A3 and Q1, I'm sure I'm going to have a vector here in which this is A3 dot Q1. This is not a vector, this is a magnitude, okay? A vector, I have to use the unit vector of this y1x. You see how it's easy, okay? A3 dot Q1, I will project that vector in this y1 axis. But this is a scalar. I want a vector, okay? Then I put Q1. Likewise, this I'll do like this. You see, look how easy. For you to understand the parallel and the parallel here. You see clearly. You see? This vector here, let's put here. This is a vector here. Okay? You see this vector here? Okay? For sure, this vector is this vector here. So, the projection of A3 on this y1 axis, I just do a dot product between A3 and the unit vector of this y1 axis. But this is a scalar. To have a vector, I just put Q1. Likewise, this vector here, first I'll get the scalar. See? The dot product between A3 and Q2, this is Q2. Okay? The unit vector, this will be this size. But I want the vector, I don't want the scalar. Then I put Q2. Now, look at the plane y1 and y2. Okay? You see this vector here? Okay? I'll put some. This vector here, okay, is in y1, y2. Okay? This vector is the sum of this vector here plus this vector. Okay? That's the resultant. Okay? Now you can see like this. Okay? For instance, this vector plus this vector is the resultant. Now this vector over here, okay, and the y1, y2 plane, okay, is the sum of this vector plus this vector. So this is a diagonal, okay, of a rectangle. Okay? Now this vector will be A3 dot Q1, the scalar Q1, plus A3 dot Q2, Q2. It's easy. Okay? Now, you see this vertical line here, this vertical line, I'll call Q3 prime. You see? It's quite clear. Look. This vector plus Q3 prime is equal to A3. Look. So A3 is equal the sum of Q prime 3 plus this resultant here, A3 dot A1 Q1 plus A3 dot Q2 Q2. Then you see clearly that Q3 prime is perpendicular to Q1 and Q2. You see? It's perpendicular. That's what I want. But Q prime 3 is equal A3, which I know, minus now A3 dot A1 Q1 minus A3 dot Q2, Q2. You see? Now, Q3, the magnitude is not necessarily 1. So, Q3 is equal the vector Q prime 3, then the square root of Q prime 3 dot Q prime 3. You see, look, the method, if you teach without being careful, you see, seems very confusing. It's very confusing, okay? But it's not. If you go step by step, knowing what you are doing, okay, then this will be easy. See? Then I get Q1, Q2, and Q3. That's orthonormal basis. Then that's right down here. Okay? Not Q prime 3. Okay? I'll modify here, put like here. Okay? Look, Q3. Because this is Q prime 3. Look. Here is Q prime 3. Okay? I don't want this, I want this, okay? Because I want orthonormal basis. Now, recall what you did in the last video. If we work with orthonormal basis, the great advantage is that the transpose is equal to the inverse. That's a very important result. That's why the method of GRAM SCHMIDT guarantees that this orthonormal basis, you see, this is a vector, okay? For instance, in R3, I have 3 components for this, 3 components for that, and 3 components for this, okay? Now, each vector, okay, when you say Q1, okay, the vector, I imagine 3 components. Okay? Likewise, A1, A2, and A3. Now, let's do an application. Okay? To find out now, it's very easy. It's easy, okay, to get orthonormal basis. Okay, solve the system of linear equations. Okay, this topic belongs to linear algebra. Okay. Now, YouTube channel Fialho Thompson. This is C as Carlos, okay? Then here, playlist created. Jordan form to have 10 videos over there, okay? Just solving a system of linear equation using Jordan form. Okay, now we use the GRAM SCHMIDT method to solve this equation. As I emphasized there on this video, the example that I show is quite simple. Okay, we can solve without using GRAM SCHMIDT method. But see, z is equal 1 here. Okay, now it's 1 here. Y is equal 1. 2 plus 5 is 7. Now 3 plus 5 is 8. So x is 1. So we know the answer. But I'm not worried about that. Okay, what I want is the concept behind the method of GRAM SCHMIDT. Okay. Now, this is my matrix A. That's my matrix A. Is a matrix. The element of this matrix are the coefficient of each unknown. So this 1, 3, and 5. Now, 0, 0, and 6. And the last row is 0, 2, and 5. Okay? Now, you see, we have here 3 columns, which are linearly independent. Okay? One column does not depend on the other two, and vice versa. Let's call A1 a vector of the first column, A2 a vector of the second column, and A3 the vector of the third column. Now, you must think why he's doing this, okay? You see at the end of this class, okay? Why GRAM SCHMIDT method is quite important to solve 100 equations and 100 unknowns. And the concept used in the 100 equations and 100 unknowns is the same way, the same method that we do right here, with this simple example. Now, let's transform A1, A2, and A3 in Q1, Q2, and Q3, like we did before, you see? Now, first, let's work in the plane, Q1 and Q2. Here I have my A1, okay? A1, this is key prime 1, okay? I coincide the method. I coincide the first column, okay, the first vector, A1 with key prime 1. And Q1 will be key prime 1 is the square root of key prime 1 dot key prime 1. See? And the coincide. Now let's calculate this. Okay? Let's calculate this. Now, you can see here that key prime 1 is a 1. Okay? And the dot product, you see, key prime, not Q1, okay? Key prime 1 is 1. So I write down 1, 0, 0. 1, 0, 0. Okay? Now, the dot product of this vector will be 1, 1, 0 times 0, and 0 times 0. So this is equal to Q1, because this dot product here will be 1, okay? So these are the components. Multiply each component, this will be 1. Okay, see the dot product? So I got the first Q1 over here. Okay, this is Q1. Okay? Now I will raise here. Let's find. So Q1, let's put it here. Q1 is equal 1, 0, 0. Okay? Now, here's my vector Q2, which I don't know. Let's put here A2. This I know, okay? I don't know Q2, but I know A2. Now, I'll project A2 right here, okay? Now, how much is this? How much is this vector here? You see, that's a projection over this straight line here. So this vector here will be A2 dot Q1 is unit vector. Now I need the vector, so I put here Q1. Exactly as I did before. So I have A2. Now A2 dot Q1. Okay? So this will be 3 times 1 plus 0 times 0. So this here, okay, will be 3. You see? I'll put here, okay, A2 dot Q1. Okay? Now, in linear algebra, you just do like this. You put A2 here, 3, 0, 2, and multiply by 1, 0, 0. So this will be the first row and first column. So it'll be 3 times 1 is 3. 0 times is 0, 2 times 0. So this is 3. This is 3. 3q1, 3q1, I just put here. So this vector here, I know that is 3 times q1. Please follow because it's simple, okay? Now, 3 times q1 will be 3, 0, 0. This here is this vector over here, okay? Here is key prime 2. So, this vector here plus key prime 2 is equal A2. So, q prime 2 is equal A2 minus 3, 0, 0. Okay? What is 3, 0, 0? I already did. This is A2 dot Q1, Q1. Okay? There's a vector. What is A2? A2 is 3, 0, 2. So this is equal 3, 0, 2 minus 3, 0, 0. See? A2 minus this here, okay? Now, 3 minus 3 is 0. 0 minus 0 is 0. 2 minus 0 is 2. Okay, this is key prime 2. Okay? Now, I don't want key prime 2. I want Q2. So, Q2 is equal Q2 prime, and this is Q2 prime dot Q2 prime. Okay? Now, Q2 prime dot Q2 prime will be, in this case here, will be 2. You know why. I'll do it here. Okay? Look. Q1 is 1, 0, 0. Let's put that. Now, let's put Q2 prime dot Q2 prime. Okay? So it will be, let's do like linear algebra, okay? Times 0, 0, 2. Okay? That's a vector. So this times this will be 4. But square root of 4 is 2. So I will divide Q2 prime by 2. So Q2 will be, see, this is Q2 prime divided by 2, because this 2 times 2 is 4. Square root of 4 is 2. So this is equal 0, 0, 1. Oh, that's Q2. That's right here. Q1, I will erase here. I already have Q2. So Q2 is equal, now 0, 0, 1. You see, the dot product between these two vectors is 0. Okay? It's good. Now I want Q3. Okay? Now I want Q3. So I erase, because it's recorded, okay, this video. Then I'll have Q3. Let's do. Again, I have a plane. Q1, Q2, this Q1. This, I have a vector here, is A3. See? Now I'll project A3 here. Let's do this. Okay? Now, I have this vector here plus this vector here. So I'll project A3 on this y1x. Okay? This will be, this vector here will be the projection of A3 on this. Let's put Q1 and Q2 here. Okay? Now, this vector here will be the sum, okay, of A3 dot Q1. That's a scalar. In this direction here is Q1, vector Q1. Plus, now this vector here, I project A3 on this y2 axis. So plus A3 dot Q2, Q2. See? Now, K prime, this vector plus this vector here, which we called K prime 3, will be A3. So K prime 3 is equal A3, that the sum of this plus this is equal this. So this is equal A3, which we have A3 minus this here, okay? A3 dot Q1 minus A3 dot Q2. I'll get here, okay? I'll calculate. Let's see. I will raise here. And let's calculate this. Okay. A3 we have. So K3 prime is equal. What is A3? A3 is 5, 6, 5. Minus. Now, A3 dot Q1. Okay. A3 dot Q1. Let's write down here. I'll raise, okay? A3 dot Q1. This is equal. This A3. I'll put A3 is 5, 6, 5 dot Q1, 1, 0, 0. Okay? Now, this row times this column, so this will be 5. Okay? So, this is 5. 5 Q1. Okay? Now, A3 dot Q2. A3 dot Q2. I already have Q2 here, so this will be A3 dot Q2. Then Q2 is 0, 0, 1. Okay, this row times this column. This will be 5 times 0 plus 6 times 0 plus 5. This is also 5. Now, I will write down this right here. Right here, I have this. The same thing as I did before. Okay? So, Q3 is equal. Now, 5Q1 minus 5Q1, 5, 0, 0, minus 5Q2, you see, minus 0, 0, 5. Okay? You see, now this gives me Q3. Okay? Now, 5 minus 5 is 0, minus 0 is 0. 6 minus 0 is 6. Now, 5 minus 0 minus 5 is 0. Oh, then I have K prime 3. Now, K3 is equal to K prime 3 divided by the size of K prime 3, which K prime 3 dot K prime 3. Now, you see, if you let's do this, okay? K prime 3 is 0, 6, 0 times 0, 6, 0. This is 0 times 0, 6 times 6 is 36, and 0 times 0 is 0. So this is 36. Now, the square root of 36 is 6. So I'll divide K prime 3 by 6, you see? Then I'll get 0, 1, 0. See how it's easy? Now, Q3 is 0, 1, 0, okay? Now, 0, 1, 0. Q3 is 0, 1, 0. Q3 is 0, 1, 0. You can see that they are orthonormal. You see? The magnitude is 1, U1, 1. So the dot product Q1, Q2 will be 0, okay, because this 0 here reach this one here, and vice versa. So they are orthonormal bases. Orthonormal bases. Now, let's see. Okay, look. We are working in R3, the space. Because now I can express each vector. Let me explain to you. Okay, this is already wrote. Okay, you already know this. Okay, now what is a span? Okay, now I have three vectors here. Okay, this vector and this vector and this vector. Okay. They are linearly independent vectors. I can express any vector in terms of Q1, Q2, and Q3. Okay? They must be linearly independent. They don't have to be orthonormal. Okay? In this case, it's orthonormal. Okay? If I have three vectors linearly independent in R3, okay, any vector can be written as a linear combination of these three vectors. Okay? So let's do with each column of A. You see why I'm doing this, okay? You're gonna see why. Okay. Suppose here is A1. So A1 is a linear combination of these three vectors. Let's put R 1, 1, Q1, this is a number, okay? A scalar. Plus R, 1, 2, Q2, plus R, let's put 2, 1 here, I'll tell you why. Plus R, 3, 1, Q3, okay? So this is a linear combination between these three vectors, okay? Now let's put A2 here, okay? So A2 is R 1, 2, Q1 plus R 2, 2, Q2 plus R 1, 2, 3. 3. In this case, 1, 2 is 1, R3, Q, let's put here, 3, 2. Okay, 1, 2, 2, 2, and 3, 2. Okay, there's always 2 here. Q3. Okay? Now, let's put A3 here. It's a linear combination. A3 is equal R 1, 3, Q1 plus R 2, 3, Q2 plus R 3, 3, Q3. Okay, there's a linear combination. I have a vector, a column vector, okay? Each one I can represent as a linear combination of this here. Now, all of this we did before, okay? So, instead of having Q2 prime divided by its magnitude on the left-hand side, I just put on the right-hand side, this is A2, okay? This is A1, okay? Coincides with Q1 on this case. Here A2, okay? So I divide both members by the size of Q2. This here, okay, is Q2, okay? Because Q2 prime divided by the magnitude. Okay? Likewise, the same here. Now, pay attention on here and here. Okay, look. A1 is equal Q1. Look at here. A1 is equal Q1. So, this is 1. This is 0, and this is 0. You see, A1, there is no Q2 here, no Q3 there. you see, because this coefficient, they are 0. Now, look at here and look here, okay? Look, there is a Q1 here and Q2 here. Here, there is Q1 and Q2. So, R12, R22 are different from 0, but R32 is 0, because on A2 there is no Q3. This A3, it has Q1, Q2, and Q3. You see, Q1, Q2, and Q3. You see? Look, now I'm going to write the matrix Q and the matrix R. R23 is 5, okay, here's 5. Because you see, the third row times the third column, this one here reach R23 over here, so it's 0 times R13, 0, 1 times R23, and 0 times R33. So third row, third column, look, third row, third column is 5. So R23 is 5. That's okay, that's R. Now, look here. Here is my what I want to solve. The matrix A, we say, is decomposed on this product here. Matrix Q times matrix A, R. This matrix A, okay, here is equal. Then matrix Q and this matrix R. You can see, now you must know how to multiply matrix, okay? Now, first row, first column, this will be 1, okay? Now you multiply here and compare here, okay? Now, this is equal. Now, let's do first row, first column, this will be 1, okay? Compare with matrix A, so this will be 1. That's okay. Now, second row, and in this case, second row, first row will be 0, so that's okay. Now, third row times first column, this will be 0. Now, let's go this way, okay? Now, first row, second column, this is R12, okay? R12 plus 0 plus 0. So R12, you see the position, first row, second column. Look, first row, second column is 3. So R12 is equal to 3, okay? Because this product must be equal to that. So I know the first one, okay? Now, second row and second column. This will be 0 times 0, 0 times 0, 6 times 0. So that's okay. Okay. Now, third row, second column. Okay. Here, 0, 2 R2. Okay. Here, there. I multiply. I'm sorry. I multiply here. This times this. So it will be 0 times 0 plus 0 plus 0. It's okay. Now, third row, second column. You see, look, third row, second column. 0 times R1 is 0, 1 plus R2, okay? Look, third row, second column. Look, third row, second column. So R22 is equal to, okay? Then I get, now let's see this. First row, second column, okay? This R13, okay? Look, first row, third column. First row, third column is 5, so R13 is 5. Now, second row, third column. So, second row, third column, this will be R33. Second row, third column will be 6. So, R, second row, third column. So R33 will be 6. R33 will be 6. Now, third row, third column. This is 2 R23, okay? In this case, plus 5 R33 has to be 5. You see here. Let's multiply. I'm sorry, I'm doing this, okay? Look, third row, and third column, 0, R23, and 0. So R23 is 5. R23 is 5. Now I'm ready to write R, okay? R is equal, R11, okay, is 1. This is 0, 0, okay, this is 0. Okay, now the diagonal, okay, R22, R22 is 2. Now, R33 is 6. R12 is 3. R23, 3. Now, 2, second, and 3, this is 0. Now I need R13 is 5. 5. I have AX is equal C. The elements of A are the coefficient of each unknown, x, y, and z. This is my vector x, we are called x, y, and z. This known vector is C, which is 9, 6, and 7. Now, AX, I know that A is QR, so QR, okay, this A. X is equal C. You see, now comes the great advantage of this matrix Q, that multiply by Q transpose on the left hand side. Q Rx is equal Q transpose times 6 times C. This is I, because Q transpose is the inverse of Q, because Q is Q1, Q2, Q3, so are the standard basis. So Rx is equal Q transpose times C. Now, I have Q. I'll multiply Q transpose times C. Rx is equal Q transpose times C. This is Q transpose. Q transpose. This is C. This product will be 976. Okay? So this is 976. So this Rx, this R, this is X is equal, let's call here D. Okay? Let's call D. Okay, this is equal D. Okay? Now we can get the result. You see here, in this case, the third row times the first column, 0x plus 0y plus 6z. 6z is equal 6. Z is equal 1. Okay? Now, 0 times x, 2 times y, plus 6 times z is equal 7. So, z is 1, 5 times 1 is 5, go to the other side, 7 minus 5 is 2, so y is equal 1. Okay? You see 2 times 5 is equal 7. The third equation, x plus 3y, 3 times y, plus 5 times z is equal 7. Okay? Now, this is equal, is equal 9. 9. Okay? This is 9. Okay, the first row here is 9. Now, 3 plus 5 is 8, so x is equal 9 minus 8. X is equal 1. So, we solved. Now you say, it's very, very complicated, okay? Doesn't matter, okay? The computer will do this. It's just for you to know an application of GRAM SCHMIDT.